I decided to use more user-defined functions in this program to make it more cleaner, so I'll begin by declaring function prototypes. I'll declare matrix addition prototype that will accept two matrices and print the added value of them. I'll then declare matrix subtraction prototype that will accept two matrices and print the value of their subtraction. I'll then declare matrix multiplication prototype that accepts two matrices and prints the value of their multiplication. I'll then declare matrix transpose prototype that accepts a matrix and prints the transposed version of it. I'll then declare find solutions prototype that will print the solutions of simultaneous linear equations in matrix form. In the matrix addition definition, I will define matrix addition to accept matrix 1 and matrix 2 as two arguments to the function. I'll declare matrix sum to be a matrix with the same rows and columns of matrix 1. For each value in matrix 1, I'll add the corresponding space value of matrix 2 and store in the corresponding value of matrix sum. If the column number exceeds the number of columns in matrix 1, I'll move to the next row. If the row number exceeds the number of rows in matrix 2, I'll stop the summation because all of the values would have been added. I'll finally print matrix sum by printing this character, and for every space in matrix sum, I'll print the current value. If the column number exceeds the number of columns in matrix sum, I'll print this character, and I'll move to the next row and print it again. If the row number exceeds the number of rows in matrix 1, I'll stop printing, because all of the values of the matrix would have been printed. Now I'll define matrix subtraction. I'll define matrix subtraction to take two arguments, matrix 1 and matrix 2. I'll declare matrix difference to be a matrix with the same rows and columns of matrix 1. For each value in matrix, I'll subtract the corresponding space value of matrix 2 and store in the corresponding value of matrix difference. If the column number exceeds the number of columns in matrix 1, I'll move to the next row, and if the row number exceeds the number of rows in matrix 2, I'll stop the subtraction because all of the values would have been subtracted. I'll finally print this matrix difference. I'll print this character, and for every space in matrix difference, I'll print the current value. If the column number exceeds the number of columns in matrix difference, I'll print this character and move on to the next row and print it again. If the row number exceeds the number of rows in matrix difference, I'll stop printing because all values would have been printed. Now I'll define matrix multiplication. I'll define matrix multiplication to be a matrix that accepts two arguments, matrix 1 and matrix 2. I'll declare matrix product to be a matrix with the same number of rows of matrix 1 and the same number of columns of matrix 2. I'll declare integer variable sum to temporarily store the sum of each multiplied value. For every space in matrix product, I'll multiply the corresponding row of matrix 1 by the corresponding column of matrix 2, doing this by adding each product to sum. Once the last row is reached in matrix 2, I'll store sum in the corresponding value of matrix product. Once the last row of matrix 1 is multiplied by the last column of matrix, I'll stop billing matrix product. I'll print matrix product using the previous print methods described for the previous functions. I'll define matrix transpose to be a function that takes one argument matrix, and I'll declare matrix transpose with the number of rows being the number of columns in matrix and the number of columns being the number of rows in matrix. I'll fill each column of matrix transpose with the corresponding row of matrix. For each space in matrix transpose, I'll fill with the reversed row and column value of matrix, and I'll stop filling this matrix once the last space is filled. I'll then print matrix transpose using the previous print method described. Next, we will define our last function, find solutions, using Cramer's rule. So we'll define find solutions to take two arguments, matrix 1 and matrix 2. We'll declare a variable named determinant to store the determinant of matrix 1. If matrix 1 is a 2 by 2 matrix, we'll find the determinant using the 2 by 2 matrix procedure. We'll multiply the first value in the first row and column of matrix 1 by the value in the second row and column of matrix 1. We'll subtract the product of the value in the first row and second column and the value in the second row and second column. We'll store this in determinant. Otherwise, the matrix will be a 3x3 matrix, so we'll follow 3x3 matrix procedure to find the determinant. So we'll declare M1, M2, and M3 to be 2x2 matrices. We'll declare D1, D2, and D3 to be variables to store the subdeterminants. We'll assign M1 the values of matrix 1 with the first column and first row removed. We'll assign M2 to be the values of matrix 1 with the first row and second column removed. Finally, we'll assign M3 the values of matrix 1 with the first row and last column removed. We're going to find the determinants of these subdeterminants using 2x2 matrix procedure. We're going to store this in D1, D2, and D3 respectively. We'll multiply the value of the first space in matrix 1 by D1. We'll subtract the product of the second value of matrix 1 and D2. And we'll add the product of the third value of matrix 1 and D3. And then we'll store these operations in determinant. Next, declare matrix X to be matrix 1 with the first column containing matrix 2. Declare matrix Y to be matrix 1 with the second column containing matrix 2. If matrix 1 has 3 rows, declare matrix Z to be matrix 1 with the third column containing matrix 2. Find the determinant of matrix X, matrix Y, and matrix Z only if matrix 1 is a 3x3 matrix. Otherwise, only find the determinant of matrix X and matrix Y. Declare a variable X solution and store the result of dividing matrix X by determinant. Declare a variable Y solution and store the result of dividing matrix Y by determinant. If matrix 1 is a 3x3 matrix, declare a variable Z solution and store the result of dividing matrix Z by determinant. I'll print X solution and Y solution, and if the matrix is a 3x3 matrix, I'll print Z solution. Now we will set up variables for the user prompts. We'll declare local integer variables A rows and B rows to store the number of rows in the matrices. Now we'll declare local integer variables A columns and B columns to store the number of columns in the matrices. And we'll declare local character variable valid matrices to store the value of whether both matrices are valid. And we'll assign n to this, and we can change it later depending on how the program goes. And then we'll declare character variable choice that will store the user's choice throughout the program. Now we will prompt the user and create the matrices. I'll prompt the user for the desired matrix calculation/manipulation and store in choice. An input of A will signal matrix addition, an input of S will signal matrix subtraction, an input of M will signal matrix multiplication, an input of T will signal a matrix transpose, and an input of L will signal finding solutions to matrix coefficients. To ensure the desired matrices are valid, I'm going to do the following while valid matrices is equivalent to n. I'll prompt the user for the number of rows in matrix A and store in A rows. I'll prompt the user for the number of columns in matrix A and store in A columns. If the choice is equivalent to capital T or lowercase t, I'll exit the loop because we only need one matrix. Otherwise, I'll prompt the user for the number of rows in matrix B and store in B rows, and prompt the user for the number of columns in matrix B and store in B columns. If the choice is equivalent to an A character and an S character, I'll check if both matrices have the same number of rows and columns. If this is true, I'll set valid matrices to Y. Otherwise, I'll inform the user of a matrix mismatch and skip to the next iteration, which will prompt them again. If choice is equivalent to capital M or lowercase m, I'll check if A columns is equivalent to B rows. If this is true, I'll set valid matrices to Y. Otherwise, I'll inform the user of a matrix mismatch and skip to the next iteration. If the choice is equivalent to capital F or lowercase f, I'll check if A rows is equivalent to B rows and B columns is equal to 0. If this is true, I'll set valid matrices to Y. Otherwise, I'll inform the user of a matrix mismatch and skip to the next iteration, which will prompt them again. I'll declare local matrix A with A rows and A columns. If the choice is not capital T or lowercase d, I'll declare local matrix B with B rows and B columns. Now I'll fill the matrices. For every space in matrix A, I'll prompt the user for a value and store the user's inputted value. If the column number exceeds A columns, move to the next row. If the row number exceeds A rows, stop retrieving user input because we have filled the matrix. If the choice is not equal to capital T or lowercase t, I'll go ahead and fill matrix B. So for every space in matrix B, I'll store the user's inputted value. Print the matrices for the user using a for loop with the same print method described in the other functions. Finally, we will perform the correct matrix operations based on the choice that the user has provided, and we will execute the corresponding functions. Finally, the program will end.